Welcome everybody. We're going to talk about the basics of machine learning. This is a little bit theoretical presentation. It's not a practical presentation. So if you're looking for very practical advice, I'm sorry, it's not in this session. Next year, if you invite me back, it will be practical. But this year, it will be theoretical because I believe that you have to know the theory before going to practice. And that's why we're talking about the theory. This is my first time in DevOps and my first time in Morocco, actually. Well, I've been visiting Morocco when I was a child, and I remember the tea, and I still love it. So when I came here, I said, do you still have the tea? And they said, what tea? I said, the Moroccan tea, the mint thing. Yes, of course. I was like, it's still as good as I remember. So yeah, I love the tea. And I'm a coffee person, so this is very serious. I really love your tea. So anyway, back to the topic. Since it's my first time here, you don't know me yet. And since it's my first time also in DevOps, nobody knows me. So it's better I tell a little bit about myself. So I have graduated from University of Helsinki. I have a master's degree in computer science. I'm specialized on information systems and databases. That's what I do. At the moment, I'm actually doing my doctoral studies. I'm doing my PhD, and it's related to this kind of topics that I'm talking about today. I also teach at the university. And I have very good students. I'm very proud of them. I just evaluated the exams, and they were very good. So I'm very proud of my students. I'm also a CEO for a company, which is a consulting company in Finland called Miracle. And my apologies for the slides because I gave this presentation somewhere else earlier and didn't have the time to change to the other template. So apologies for that. But that's my company anyway. It's a very small one, and we don't work here. So I'm not trying to make it a commercial thing here. No. So I'm a CEO for a company. Actually, I'm a CEO for two companies, but it doesn't count. Anything to do with data and databases, that's something I really love. And that's one of the reasons I like machine learning a lot, and I like to tell you about machine learning as well. I'm an Oracle ACE Director, which is an award from Oracle, and also part of that award is that I go and talk. I have written a couple of books, I've been talking and so on, so that's part of that job. I'm also an ambassador/spokesperson for EMEA user groups, EMEA Oracle user groups. So I'm very active in the Oracle user community. I'm a speaker and author. I already mentioned I wrote some books. Here are my books. The first one is about database designing, which I wrote by myself. It was a very fun project. I enjoyed a lot. And during that project, I learned that my family knows how to cook. I have two sons, tall like this, and I have a husband who's actually here. And during this project, I learned they know how to cook because I was so excited about my book, I forgot to cook. And they were like, Mommy, I'm not going to have lunch today. And suddenly I had lunch served to me. I was like, wow, you know how to cook. So write a book and you will find new things from your family. The second book I wrote with other ACE directors, very international book because we are all from different countries and continents. That was also a fun project because we have different backgrounds, different cultures, different everything. It was really fun. I will talk about this book later in this presentation because this is touching a little bit about machine learning as well. So as I mentioned, I'm an ACE Director. There's a slide about what is this ACE Director program or the ACE program. If you're interested, there's a link about the program. But let's go to the topic finally, the machine learning. What on earth is machine learning? It's a very important part of artificial intelligence. So it's a very crucial part of that. Machine learning teaches computers to learn from experience. So we learn from experience, but so do computers. The experience for computers is algorithms. They use algorithms and data to learn. It's about a lot of things. It's not just one thing, because usually people say, oh, machine learning is mathematics, and I'm not good in math. But it's a lot of other things as well. It is, of course, about mathematics and statistics and so on, but it's all about a lot of other things as well. So don't think if you are not good in math, machine learning is not for you. Not true at all. Okay? So the machine learning is about learning from data and algorithms and making predictions about future. So everything machine learning is doing is predictions and approximations. It's not the truth. So whatever we get from there, it's just suggestions what we should be doing, or we could be doing. In 1959, so this is not a new thing, this is an old thing. 1959, Arthur Samuel already said that this machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. So a lot of people think machine learning is something new and cool. It's very old and dusty, seriously. But it's just very important nowadays because we need machine learning. I will explain you later why. So it is a systematic study of algorithms and systems that improve their knowledge or their performance with experience. That's what machine learning is about. So why do we need machine learning now? 1959 and this year, long gap. Well, we have improved technology. So those years when this guy here, Arthur Samuel, was doing his research on machine learning on check play, he didn't have the technology we have. So we have so much improved technology compared to those times. He didn't have proper computers. We have all that now available, so we are able to use machine learning. He was not really able to use it. The price of storage solutions has gone down, so it's not so expensive anymore. And so many other good things that has happened during those years that we are able to do machine learning nowadays. And it's not the only thing. The other thing is also that the environment where we live now, it needs machine learning. Because we need to be fast, we need to know more, we need to be better than the other companies in the area, and so on. So we really need machine learning to be good, to be better than the others. So we have the technology, but we also have the need for machine learning. So it's about artificial intelligence, as I said. It's part of that. But one pressure comes from big data. So everybody's talking about big data, and that's one of the reasons why we need machine learning. But what is this big data? Oh, do you want to have a picture? Please do. So what is this big data? Well, there's a lot of definitions for that, but I just kind of put myself here, by my own definition here, because I hate this word big data, because it implies that there's a certain size of data when it becomes big. When it's smaller than that, it's medium, and when it's smaller than something, it's like small data. But it's not about the size. There is no particular size you can say, now it's big data. Okay, it's of course about the size as well, but it's not really all of it. So the word big here means that we are not able to use the traditional ways of handling the data we've been using before. So we need to have a new ways of handling data so that we are able to do it. Examples like we have an attachment in an email, but we can't open it for some reason. Or we have a photo, we usually edit the photos, but this particular photo we cannot edit. That might imply that we are talking about big data. It's somehow different than it used to be. There's always these 3 V's people say when we talk about big data. 3 V's. First, of course, volume. So the size of the data. It has to be a lot of data. There's some seats here available and one here. Just come in. I'm sure you will find seats. Welcome. So the volume is, of course, important. But there's also velocity, which means the speed. So the data is coming very fast. We are already processing the data when there's more data coming in. So it's very hard to find a time. It's actually impossible to find a time when all the data is in. And now we can run the report. The data is coming in all the time. That's what velocity is about. And it's also about variety. We have different data models, and we have to accommodate all of them. So it's not just about relational data. It's also about semi-structured or unstructured data that we have to be able to handle. And one solution for this last thing is a thing called multimodal database, which is one of my research topics, but I will not talk about it today. But it's one of the things we have also in big data, to have different data models that should be handled as well. But it's about more V's, the big data. It's all about veracity, which means that uncertainty of the data. So some data in my billing system, my invoicing system, I know exactly this customer got this invoice, did not pay it by this time, so I send another invoice, and so I know exactly what's true and what's not true. But in the big data world, I have so many data sources. I can't trust all of them. Some of them can be even harmful to my data. So uncertainty of the data is an issue. It's also about viability. which means that we need to validate the hypothesis before taking further action. And in the process of determining the viability of the variable, we can expand our view to determine other variables. So it means like, if I say, because of this black thing here, tomorrow will be a great weather. They are not related to each other at all. But the computer might say, whenever you have this kind of black thing on a table, the next day the weather has been perfect. But I, as a human being, I know there's no correlation between these two facts. The weather can be whatever. If I have this here, I don't have it on my table. So this is what it means. Somebody has to validate if it's really something that is worth investigating or not. The value is very important. So some data is very valuable and some data is not valuable at all. And what makes it very tricky is that something that is not valuable today at all can be tomorrow the most valuable data we have in a company. So the value can change during time. Even in my company, not just the whole world, but in my company, something can be very valuable tomorrow, not valuable today, or the opposite. And it's also about the variability, which means it refers to the data whose meaning is constantly changing. Like in a sentence, you have a word doing, and in front of doing, you put not doing. So the meaning changes. So depending on the context, the word means something else. The same goes with data. Depending where the data comes, what's together with that data, the meaning can be completely different. So handling this data is not easy because all of this complexity. And last but not least, visualization. Visualization is very important when we have large amount of data, different kind of data, and so on and so on and so on. So if we are not able to use visualization to show the data, it's very hard for human eyes and human brain to understand the data. So visualization is a very important part of big data world. So the challenges we just talked about, we have more and more data, the volume. This is something in 1959 they didn't have. The amount of data is so much bigger than it was that time. Different data models, different data formats, loading in progress while we are already processing it, and not all the data is reliable. We do not know what we are looking for. So we have plenty of data and we are asking the system, give me some knowledge from the data. I don't know what I'm looking for, but tell me something. And then I decide if it's interesting or not. And also, we must support end users who are not technical at all. So it cannot be something you need to use a programming language to get the knowledge from data. You have to have visualization to be able to let those people, like journalists or politicians or whatever non-technical people, to find the knowledge from the data, because they need the data and they understand it better than technical people. So we have to have tools for them to use the knowledge, use the data. But the problem here is all this must be done very fast and efficiently. It cannot take hours or days or months or years to process. It must be done fast, because this journalist is waiting for the knowledge very fast, or the politician wants to know something to make the decision, or the CEO of the company needs to know something to be able to make the decision how the company will continue from today. So it must be very fast. And because of that, we need to use machines, because people are not as fast as machines. Sometimes we are faster than machines, but most of the time machines are faster. And actually machines are also cheaper than people. So it has to be also cheaper, because everybody is always saying we are saving in costs. That's how to do it. But now the next thing is people are worrying, will I lose my job? Does that mean that machines will do all my job next year? No, because in this whole thing, which we will talk about in this session, there's a lot of phases which computers cannot do alone. The computer needs the human brain to solve things, to tell if it's important or not. Does this really affect if it's going to be sunny tomorrow or not? This kind of things, because the computer is only seeing data. It doesn't have the knowledge we have, even though it's learning all the time. So there are a lot of places where we have the knowledge the computer will never reach. So don't worry, you will be needed. And as I said, it has to be done fast and efficiently. The computer can't do it without you. So there always has to be people working with computers. But the computers will help you so you can just do more important and more fun jobs. And the computer will do the boring job. So when can I use machine learning? Number one, you must have data. This sounds very stupid, I know, but it's a serious thing. I was trying to build a demo for one of my presentations, and I started with a very lousy data. And I never managed to build the demo because of the data. The data was not enough, it was bad quality and so on. So number one is have data, enough data, good enough data. So without data, this is no point, okay? It sounds silly, but it's really, really important. We can't perform any kind of machine learning without data. And part of this data is used for teaching the computer, so for the learning, and part of the data is used to really show that what the machine learned is true. So part is for finding the model, and part is to prove the model works. So you don't use all the data to teach the computer. You save part of the data to show that it really learned something. Whatever it's giving you makes sense to you as well. So the rules and equations are very complex. That's a good sign of using machine learning. If it's a simple rule, it's easy to program. But if it's very complex, machine learning might be the solution. Like image recognition is one of those classical examples. And if the rules and equations are constantly changing, that might be a sign of using machine learning. Because how would you adapt for everything if you don't have machine learning to learn? Like fraud detection, like spam filters, very classical examples of things where the rules are changing all the time. So the nature of the data changes, and the program must adapt to that, kind of automatically. Like I said earlier, something that is very not important today at all, some data, might be very important tomorrow. Today's spam might be tomorrow's ham. So the change of the data's nature can be very dramatic. And it actually should adapt to that as well. So some real-life examples of machine learning. What is it? By the way, ML here says machine learning. I'm too lazy to type everything. So ML is machine learning. So spam filter is a very classical example. You can't program spam filters because they are changing constantly. There are always new rules and so on and so on. If you try to program that, you will have 5 people in your company working on that. And what's the point? Your company is not a spam filter company. So machine learning is for that. It's adapting for all the changes automatically and filtering the spams it learns that is a spam. For example, whenever this email comes, a lot of people put it immediately to the rubbish bin. It could be spam. So there's different kind of rules it can be using to learn what is a spam and what is not a spam. Log filters or log alarms, data analytics, image recognition, speech recognition, medical diagnosis. I especially love medical diagnosis because that could mean that before I get sick, the computer would already say, oh, you might get sick tomorrow because you have this and that. What should you do? And if there's something I can do to prevent being sick, that would be very great. Or if it's something very, very dangerous that can be found before it gets dangerous and healed before that, that would be very great. So I really look forward to that part. Robotics, it's also very interesting, and especially with people who are not so excited about the theory, that shows the practice very practically. So robotics is also a very interesting area of machine learning. But remember, as I said in the beginning, it's always about approximation. So machine learning is not giving you the truth. It's not telling you when this thing is here, tomorrow is sunny. And then tomorrow you're wearing too little clothes because you are sure it's sunny, it's nice weather. So it's just a prediction, approximation, what might happen if this is continuing. Always approximation. Some of these approximations are better than others, and some might even be useful, but some are just completely rubbish. So just remember that there is no truth anywhere in machine learning, just approximations. We are searching for patterns and trends, and based on those, we predict something. There's a measure called prediction accuracy. The higher the number is, the better this guess is. So there are different measures you can use to validate if your machine learning algorithm and your whole model is working or not. One of them is this. How accurate is the model? How good guess it is? There are several models. You just choose the best one for your purpose, but still it's approximation. It's not true. And no correct answer. So I was thinking, so when I started with machine learning, what did I found the most difficult thing with machine learning? And I say, the words. Because machine learning is about a lot of different words that are somehow connected to each other, and I couldn't make sense how. And that's why I prepared this presentation, because I was thinking maybe somebody else is struggling with the same problem. After you understand these words, the terminology, whatever the right word would be for it, it makes it easier. Because there are so many terms related to each other and a lot of synonyms for those same words, which makes it very complicated to understand. It's a simple thing, but with all this confusion, it becomes difficult. And that's why I was thinking I will explain you some of the main terms or terminology related to machine learning. First of all, we have a task. A task is a problem that we are trying to solve using machine learning. What kind of weather will we have tomorrow? Will my flight be on time tomorrow? The email that just comes to my mailbox, is it a spam or is it a real email? This kind of tasks. Then we have an algorithm, which is the experience for this computer to learn with, and it solves this learning problem. And it produces a model. A model is an output of machine learning. The task is addressed by a model. We have different models, and I think this is one of the key things here to understand different models. We have predictive models where the model output involves the target variable, like forecast might happen in the future. Then we have descriptive models where the model output does not involve the target variable. What happened? Yesterday was rainy. And then we have prescriptive models. They are recommending one or more courses of actions and showing the likely outcome of each of those decisions. So this is the most complex one. So we have a predictive model, actionable data, and a feedback to the system to learn and to track from the outcome. So 3 different kind of models that can be used, depending what the task is asking us. What kind of task do we have? Do we need to predict something? Do we need to use a descriptive model? Or what kind of task do we have? So that's, I think, number one to understand. So these different models are based on different algorithm types. I'm going to mention some algorithms. Don't get panicked with them. I'm not going to ask you any questions afterwards. Which algorithm would you choose? No, I just put some here because when you're seeing the slides afterwards and you want to check what kind of algorithm did she mention in that point, you can see some examples, what kind of algorithms might be possible. So don't worry, I have too many things here, but it's for your own good, I hope. So we have classification models. We are classifying things. We have concept learning models, tree models, rule models, linear models, distance-based models, so how far or how close are those points from each other, and we have probabilistic models. We also have more terms here. We talk about those, all of those in detail a bit later. Features or dimensions. I mentioned earlier that we have a lot of synonyms for words, so people are using different words for the same thing, like feature or dimension, or attribute. Some people even use attribute. It means the same thing, okay? So a feature is an individual measurable property or characteristics of a phenomenon being observed, says Christoph Bischoff in his book from 2006. And deriving features or feature engineering or feature extraction is one of the most important parts of machine learning. It turns data into information that a machine learning algorithm can use. So without this, the machine learning algorithm wouldn't know what to do. So it's very important to tell the machine algorithm what are the features that are interesting for you. And this is what we are doing here. And I put all these different names here because if you want to Google more about these things later, you might want to Google all these words to find different information about them. That's why I put all of them here. So then we have methods or techniques. And this is one of the key things as well. We have unsupervised learning and we have supervised learning. Let's see how these are connected to each other. But we start with the task first. So we have a task, what we are trying to solve using machine learning. It's very important to define the task well. I said earlier you will not lose your job because we need human beings here. The task must be defined by us because we know what we are trying to find. Sometimes it takes more iterations because first we don't know what we are looking for. But when it's getting closer and closer, we define what the task is. What are we trying to find? What are we trying to do with machine learning? So it's very important. It's not only a computational subject, this machine learning. It's also very practical and very, very important to have practical side in machine learning as well. So, but it's still quite much about algorithms because that's the experience for the machine. We learn with the experience while they learn with these algorithms. It's not easy to find the right algorithm for our task. It's kind of try and error. It will take probably a while to find the right one, but it's definitely worth it to find the correct one for our task. So this is an important thing for somebody. So all these things we have in machine learning, it's not that in one person in a company is doing all of it. It might be there's several people, they have different scopes in the whole process. So somebody has this skill, somebody has that skill, and so on. So a lot of people might be working together to get this task done by machine learning. So it's not maybe just one person. So usually we try several algorithms and we try to find the best one for this particular task. So which algorithm to choose? The selection of algorithm depends, for instance, a couple of things. The size and type of the data, the insight you want to get from the data, or how those insights will be used. Just some things that might affect your decision. And it's a trade-off of many things. So the predictive accuracy on new data, so how well will it predict the future, might be very important or might not mean anything, might not be important at all. The speed of training, how fast will it learn, might be important, not important at all. Memory usage, we don't have much memory, we have plenty of memory, doesn't matter at all how much memory it's using. Transparency, some people want to understand detailed why, or some processes might also demand it. You have to know exactly why this kind of data led to that decision. So you have to understand the whole pipe, what happened, why did the algorithm did what it did. So you have to understand everything. And some just say, I don't care at all, I'm using algorithm X and that's it. I don't have to know why it's doing it, whatever it's doing, as long as my metrics show good. And that's it. So depending which one is important. And also the interpretability, the ability for us to understand what's happening. Sometimes it's important, sometimes it doesn't matter at all. The models, there are different kind of models that we can use. We have geometric models, like support vector machines, notion of distance, plenty of different kind of the models for that. Probabilistic models like Bayesian classifier, just some examples for you to Google more information. Logical models like decision trees. Decision tree is probably something everybody knows because it's very common in many, many places. So it's usually something everybody knows. Then we have grouping models. The number of groups determined at the training time. And then we have grading models, infinitive resolution. The features. The model is only as good as its features. So if we fail defining the features, you remember it was transforming the data into some kind of information the algorithm can use. If we fail with that, it's no use. So the model will not really work, or it will work badly. And also the interaction between those features, how they reflect to each other, is important. And also, just tiny little detail here in the end, you can also actually change the data before you give it to the machine learning algorithm. Of course, there's a phase where you have to check the data. There's actually a lot of things you have to do with the data. But something that is very shocking to me is that you can actually even change it. So if it says it's 11.1 kilograms, you can change it to 10 and give that 10 to the machine learning algorithm. If that is not relevant, if it's 11.1 or 10, 10 is close enough, good enough for the algorithm to use. So you can even change the data before giving it. So this is also something only you can decide. You can't let any computer decide, will we change something or not. It's you are qualifying the data before giving it to the algorithm or to the model. So there's a lot of points. I try to show a little bit of points where you are very important. So in short, what machine learning is, we are using the right features with right algorithm to build the right model that achieves the right task. That's how these words are related to each other. So in the beginning we are talking starting from task, going to feature, but this is how it goes if you think from the other side. So we need to have the right features, right algorithm and right model to really achieve the task we have. So as I mentioned, there are two types of methods: unsupervised learning and supervised learning. Usually when people teach these terms, they start with supervised learning, but I like to start with unsupervised learning. And the reason is that in a process, if you happen to use them both, you start with unsupervised learning to find the knowledge from the data. This one on the table, sunny day, not interesting, and so on. So you will find something from the data before really deciding what you're going to do with it. And for that, you are using unsupervised and then supervised. And that's why I would like to go on this order. But usually it's in the other order because supervised is more interesting, I think, probably. But I find unsupervised very interesting. So unsupervised learning is finding hidden patterns or intrinsic structures in the input data. So we have data we know actually nothing about, and we try to find something from that data. While as the supervised learning is training the model on known input and output data to predict new outputs for the new input data. Let's go to unsupervised first. So unsupervised learning is learning from unlabeled data. So we have input data, doesn't have any labels. There's no first name, last name, so on. It's just data. And we're trying to find patterns or intrinsic structures in that data. And machine learning algorithms will find natural patterns in that data to make better decisions and predictions possible. This is typically used when we don't have any specific goal, what we are trying to do. We don't have the task yet. We are not sure what information this data contains. So we are asking the machine, tell me something about the data. Tell me something that is valuable to me. Or we want to reduce the features. Remember the features, where as good as the features are, the good is your model. So we have to sometimes reduce the features to get a better model. So this can be used to reduce those features, or sometimes add the features, but usually reduce the features to pre-process before we start using supervised learning. So some things where you could use unsupervised learning. Mostly unsupervised learning is about clustering. It's the most common method for unsupervised learning. And there are two ways of doing clustering. There are two clustering algorithms. There is hard clustering and soft clustering. The difference between these two is that a hard clustering, when you have a data point, it can only belong to one cluster. While in soft clustering, this particular point can belong to more than just one cluster. And that's the difference between hard and soft. Hard, only one place. Soft can be in several places, in several clusters. So hard clustering, only one. For hard clustering, there are several algorithms. I'm not going them through. I just tell you what I put here, so when later you're checking them, you know what to find here. K-means is probably the most common one, and it's used when the number of clusters is known. So we already know we will put them in two clusters. We have spams and real emails, for instance. Or fast clustering of large data sets is needed. That's a typical use case for that algorithm. K-medoids is very similar to K-means. Number of clusters is known. Fast clustering of data, categorizing data is something we need to do. It's very similar, but it's working a little bit differently with the keyword here is medoids. That's what's different. I'm not going to details, but if you want to Google, it's very interesting. Actually, there's a very good video about this in YouTube where you can learn how it works. So very similar, but a little bit different. So these algorithms, the whole idea in all of these is we are putting things in clusters and using those clusters to find something that is very important for us. Hierarchy can be used when you don't know how many clusters we have. And when you do soft clustering, we can put them in many, many places. Not just one cluster, but 2 or 3 or 4 clusters. Fuzzy C-means is probably the most common algorithm for it. Number of clusters known, clusters overlapping, pattern recognition is a typical example. So this is how to read these slides. I don't go to details, don't worry. There are several different kind of algorithms for all of these. These are just some examples so that you can see there are plenty of options. And that's why finding the right algorithm is difficult, but that's why it's very good because you have a lot of options. If you're trying with one algorithm, you are not having success, you try with another one. And I'm sure there's always something that will work in your task. So supervised learning. The difference now is we know our data. We know what we have. We teach the machine to predict based on the data we have and based on the outcomes it has just passed with the training data. So that's what we are doing with supervised learning. And this is how the process goes. We start with training. We load the data. We pre-process data. Remember, we can even change the data here. We are the kings. We learn. It learns using a method and the algorithm. We create the model. And we go over and over until we have built the model that is the right one. Then we predict. So we just taught the machine how things work. Then we take another set of data, a new data. We pre-process like we did earlier. We use the model we just built. We get predictions. And then if we are happy with it, it was the measures we were trying to find were good enough and we like the model, we are ready to implement it to our applications and use it in our application. That's how it goes in a simple way, the whole process. We train, we predict, and we start using it. So there's two ways of doing supervised learning. We can, for the predictive models, we can use classification or regression. It sounds very confusing, but it's very simple because these are very different from each other. Classification is for classifying data into categories. Spam, real email, spam, real email, and so on. They predict discrete responses, like tumor is small, medium, large, or tumor is cancerous, benign, or person is creditworthy, not creditworthy. So putting categories, okay? Now we know what the categories are because we are using supervised learning. So like medical imaging, speech recognition, and credit scoring. I skipped that. some algorithms as well, so that you can see what kind of algorithms are available for classification, just some examples. The same logic, when to use this here. This is a short description of that algorithm. And you can go and Google more about that particular algorithm. I just skip this. We don't go to details with them. So, supervised learning, regression. That was classification, remember? Now we're talking about regression. To predict continuous responses. The changes in temperature. How will the temperature change? Based on what we know, how it will change tomorrow, next week, and so on. Fluctuation in electricity demand. Just some examples. For example, applications like forecasting stock prices, handwriting recognition, and so on. So, some algorithms for regression, linear regression, and so on. The same logic as before. You can just check from here when you are interested about those. The fact is, when we have the model and it works very well, it works for a while, but we have to improve it probably a bit later, or maybe even today we need to improve it. We have to improve it one day. And to improve the model, why should we improve it? To increase the accuracy and predictive power, maybe. To increase the ability to recognize data from noise. So we have a lot of data, but 90% is noise, 10% is only real data. So we have to really get the 90% out before analyzing the 10%. To increase the performance, it's not fast enough. We need more speed here, in some sense. Or to improve any of the measures we want to have. Some of the measures that are important to us is not good enough. We need to improve that. So, model improvement involves things like this. Feature engineering and hyperparameter tuning. Feature engineering is feature selection or feature transformation, feature extraction. Let's talk very briefly about them. I just realized I've been talking too slowly. Feature selection is also called variable selection or attribute selection, just to confuse us. But it's the same thing. It's identifying the most relevant features that provide the best predictive model for our data. And adding variables to the model could improve the accuracy, or removing variables from the model could improve the accuracy. So depending what is the situation, we might be adding or removing features. Feature selection techniques, there are stepwise regression, sequential feature selection, regularization, and neighborhood component analysis. I don't go to details with this, but so that you know, if you need to do this, these might be, or one of these might be the thing that you could be using. Feature transformation is a form of dimensionality reduction. It's used when you want to reduce the features of your data as pre-processing for supervised learning, or when the data set is very, very big. Those frequently used, it's not working anymore because the data is much bigger than it was in the beginning. So you need to reduce the features to be able to still have a model that it's working. So this kind of situations are typical examples. And as mentioned earlier, the techniques are principal component analysis, factor analysis, and non-negative matrix factorization. Very briefly what they mean. PCA means you convert a set of observations of possible correlated variables into a smaller set of value of linearly uncorrelated variables, and these are called principal components. And the first principal component will capture the most variance, the second, the third, and so on. Factor analysis identifies underlying correlation between variables in a data set to provide a representation in terms of a smaller number of unobserved variables, the factors. And the non-negative matrix factorization, which is also called non-negative matrix approximation. It's used when those model elements must always represent non-negative quantities, like a weight of a human being or something that is not non-negative. Hyperparameter tuning is a different thing than what we're just talking about. Hyperparameter tuning is because hyperparameters are parameters whose values are set prior to the commencement of the learning process. So they are set before, not during, not after, before. And we have to choose the best of those before starting to learn. It controls how a machine learning algorithm fits the model to the data. The tuning for hyperparameters is an iterative process, like any tuning. So it's probably a continuous process. You will do things and then you will do other things and so on. You set the parameters based on best guess. You aim to find the best possible values to yield the best model, and so on and so on. There are some examples of algorithms here, but a simple algorithm with well-tuned parameters is often, I would say always, better than a very, very complex algorithm. So simple is always best in machine learning, as it's, I think, everywhere in computer science. So how do we know what to tune? It always depends what we want to achieve. So what kind of measures do we need to have? What to measure? There's plenty of things we can measure. We can measure number of positives, negatives, class ratio, accuracy, ROC curve, but it all depends on how to define the performance in our particular case. So what is important in our case? And it is an experimental objective. So there is no one thing that I can say, always the important thing is class ratio. No, it depends on your use case. Which of these or any of the other measures are important? How to measure and how to understand the measures you just got. It all depends on what we were measuring, of course. And there's one example I have here about how to know if my measures are good or bad. One of the tools is cross-validation. Cross-validation, also sometimes called rotation estimation. So we have the data. We divide in, let's say, 10 parts. We use the 9 to first train the model and the 10th to prove it works. Then we rotate forward. We use 8 and 1 to test and 1 to prove. We move, we use these to test, this to prove, and so on, so that all of these pieces have done each of those 10 jobs. Okay? That's how cross-validation or rotation estimation works. And it shows that the model really works. The accuracy is high. So what to learn next? So much in machine learning to learn, really. There's reinforcement learning, preference learning, multitask learning, online machine learning. There is active learning, deep learning. Everybody's talking about deep learning, also interesting. Adaptive intelligence. There's so many areas in machine learning that are interesting, depending what you are trying and wanting to do. So I put all those names here so you can Google if that's something that you are interested in. But one of the areas, of course, is data mining. It's been there for a long, long time, and it's still there. Data mining is one of those things. If you want to know how it works, one possibility is using Oracle SQL Developer, which is a free tool. You can just install and start using it. There's an add-on called Data Miner. I put some instructions here how to take that in action, how to really use the Data Miner. So it's a free tool, easy to use, and so on. And I will put all the slides available, don't worry. And it's a graphical tool, so it makes it easier. You just drag and drop your models here and see what happens with your data that you understand. So this is one possibility. And about that, we have in our book in chapter 10. And then Brendan Tierney also wrote another book about it. So if this is something you're interested, fine. In Oracle database, we also have the R. R language is interesting for many people. Even my son knows R. And yes, he's studying computer science at the university, so that's understandable. So R is quite interesting. That might be a solution if R is something you either need to learn or you already know. In our book, we have one chapter about this R in Oracle database particularly, and then Brendan wrote another book about it as well. Then in Oracle database, we have a thing called predictive queries that can be also used for this kind of understanding my data things in our chapter 12. But if you're not interested in any of those and they kind of feel a little bit distant to you, don't worry. We have Python, we have C, we have C++, we have Java, JavaScript, Julia, Scala, Octave. We have plenty of other things where you can do the same thing. So I would advise, take the one that is something you already know, because machine learning is new, but something from here is already something you know. Put them together, because all of these languages, they have libraries for machine learning. So add something you already know to something that is new, and it makes a lot of sense. So depending on what you already know and what you would like to learn, choose some of these. And I put a link here about languages that are found most popular. If you are curious, you can go and click it. It's these languages anyway, so probably you already know those languages, so no big deal. But anyway, the machine learning is here. It's now and it's the future, so it's really worth putting some effort. So I really encourage you to do that, because artificial intelligence and machine learning are here. It's a very good currency when you're looking for a new job and so on, so it's a good thing to know. And there's so many interesting areas to learn. It's not just about one thing, and if that's not interesting to you, it's not to you at all. There are so many things in machine learning that I'm sure there's something that is exactly your thing. So just take a look. Pick your thing and start learning. The time is here, and it's also in the future, so you are investing to your future. Remember all the V's. They bring pressure for machine learning. All these use cases, starting from spam filters, going to the medical diagnosis, there is no business where machine learning is not useful. It's everywhere. But remember, it's about approximation. Don't take it as a fact. It's an approximation of something that might happen. We talked about unsupervised and supervised learning. We talked about predictive models, classification and regression. We talked about how to improve the model using feature engineering or hyperparameter tuning. We talked about you have to know what you are measuring to know if your model is really working or not. And so much to learn about machine learning. I really encourage you to go and learn. Thank you so much for attending, and if you have any questions, this is my email and my Twitter handle. Thank you. I should have like 2 hours to talk. 15 minutes is too short.